welcome to my talk about GPU crash debugging. Before I start, could I get maybe a show of hands who of you have already had experience dealing with GPU crashes? That's a lot of hands, that's good to know. I see it's a big problem. But if you don't worry, I'll try my best to explain what they are so you won't be confused during the talk. So crashes on the GPU, they're quite opaque and they require specialized knowledge to debug. Little information is usually available and debugging them is a bit of an art. So with this talk, I hope to provide some tips as well as present some tools and techniques to make it easier to debug them in Unreal. So first, a little bit about me. I'm an engineering manager at CD Projekt Red. I joined the company to work on the next Witcher in Unreal. Before that, I briefly worked as a GI researcher on the Open3D engine, but most of my career I spent as a rendering engineer working with Unreal. So let's start with something familiar, a CPU crash. A CPU crash is by no means easy to debug. But there are some ways that CPU crashes are easier than GPUs. If a crash happens on the CPU, you immediately get a crash report, all threads are interrupted, and you can inspect the state of the program at the moment of the crash. Now let's move to a GPU crash. A GPU has way more threads running at the same time than a CPU. This means that when a fault happens on the GPU, it can take a while before we actually get back that a crash has happened. So the crash report may actually happen a long time after the actual fault on the GPU happened. It can actually take more than 2 seconds between the actual GPU fault and the crash report. This has some consequences for what information we get back. When we get the crash report, we may get incorrect information on the state of the GPU. This is because the GPU keeps executing, and it may be that some of the jobs that were active that hadn't even started at the moment of the crash are active when the report happens. It also may be that some jobs have finished, and there's really, unless you have more accurate information, no way of knowing which active job actually crashed the GPU. Now let me explain what Windows TDR means. TDR stands for Timeout Detection and Recovery. It's a system in Windows to detect when a GPU is hung and when it needs to stop execution or the program would freeze forever. This is called a timeout. When it happens, the GPU resets and the process crashes. Obviously, this is a bad thing, as for the GPU to run well and things to appear smooth, any work submitted should finish quickly and be small. The other reason a GPU crash can happen is in the case of a page fault, which means there was an invalid memory access, much like an access violation or null pointer exception on the CPU. For this talk, we will mostly focus on crashes on PC, though the concepts translate to other platforms. The most obvious cause for a timeout is infinite loops, a shader that never ends. This will hang the GPU, as at some point work must finish. Another cause is incorrect synchronization. If the GPU is instructed to wait, but never receives a signal to continue, it will hang. Also very slow shaders, especially shaders like ray marching or ray tracing, can hang the GPU. If they take a long time to finish, they may cause a TDR, even if they would eventually finish. If you run out of physical memory, that's also a reason why the GPU may crash. If it needs to start swapping, everything will slow down a lot and cause a crash. It may also be that there's a bug in the driver, which causes a timeout, in which case you will get the same error. So let's go a bit more into a synchronization bug. In The Witcher 3 Next Gen, we had a weird synchronization bug. It was actually not that complicated. A fence was simply missing a signal. But the weird part was that no TDR would trigger. So essentially, the program would just freeze forever, which would happen if there was no TDR in place. We had to manually figure out what was going on using custom commands to the GPU to see why it was hanging. Another timeout we had was in a cinematic. Our cinematic team had a crash in Sequencer. Rendering a single frame could take a few seconds to complete because they were using the highest quality and unlimited view distance. Obviously, it would result in a TDR because that would take multiple seconds and it's not suitable for offline rendering. So to fix that, we actually just increased the TDR delay, because for that case, offline rendering, it's actually fine for the GPU to take a bit longer. But this is really the exception, as you wouldn't want to do this in anything that's real time, as it would hide actual issues. So I would recommend not changing it unless it's for something like offline rendering. So let's now move on to page faults. With DirectX 12, we are now allowed to do very precise memory management, but this also introduces the risk of invalid memory accesses. If we access an address of a resource that is evicted, the GPU will crash. There can be a big delay between the actual fault happening and the crash report, so it's good to be aware. Here's an example of a page fault we had on PS5. We had a GPU crash. We were able to use extra information to track it down to a single material that was for a specific mug. It used a complex material and was sampling multiple virtual textures. A good hint was that we had just upgraded the engine, and as many features are still being worked on, we found that the cause of it was the virtual textures. We found a workaround and waited for an actual engine patch to fix the issue with the virtual textures, and then the issue was resolved. So now you know what a GPU crash is, but what can you do about it? We'll go over how to approach such an issue and what tools are available in and out of Unreal to help with these kind of problems. Unfortunately, the process of debugging a GPU crash is not as well documented as the CPU equivalent. So let's see what we can do. Let's start with a sanity check. Make sure your driver is updated, because as I said, this could cause a crash and you would be wasting your time if you were to investigate that one. Make sure also that your GPU is strong enough and has sufficient memory, especially with the new features of Unreal and new features such as ray tracing. It's good to make sure that your GPU can handle the right settings. And in Editor, the process is even heavier. Make sure to check your quality settings. Make sure that not the whole world is in memory at the same time, as these things can obviously lead to the GPU running out of resources and crash. There might be also heavy background processes going on, such as an offline render, which can eat up resources and cause a crash to happen. So how do you set up Unreal for debugging these crashes? Well, first there is a simple flag called GPU Crash Debugging. This will enable all available tools to add extra validation and tracking what's going on the GPU. There is, however, a performance overhead, so you might not want to enable this flag by default. Later, we'll go into each of these tools and how to use them and what are their advantages. Then there is the command line argument d4d debug. d4d debug is great for verifying if there's malformed d4d commands, which may result in a crash. But it's important to keep in mind that this validation happens on the CPU. There's no validation happening on the GPU, so it's not able to test for certain errors, as it simply doesn't have all information. It's still an easy and quick way to catch errors. For extra validation, you can enable the GPU validation flag. This instruments shaders to do additional checks. This can catch errors that aren't detectable on the CPU. It can catch incorrect descriptors, references to deleted resources, or indexing beyond the end of a descriptor heap. All of these could cause page faults. Another useful tool is to enable extra events. If you want to know exactly which material or mesh caused the GPU crash, it's good to enable material and mesh draw events. This will include information for each draw call for crash debugging and profiling, but be sure, as it comes with a big performance price. It also shows up in the GPU profiler, which is very useful if you want to profile individual materials or meshes. And remember the mug from earlier? We could very easily track that down simply by enabling the mesh events. There's another CVAR you can enable to track more allocations in case of a page fault. The previous mentioned GPU crash debugging flag also enables this. So if you use one, you don't need to use the other. If you see an active resource that's reported in the crash, but it doesn't seem to be very much, you might want to enable the CVAR, as it will track all the resources that are allocated on the GPU. Below you can see an example of an active resource that Unreal reports based on the page fault address. It includes a range of 16 megabytes around the fault address. This may help find out-of-bound access as you're indexing beyond the end of a resource. Unreal also tracks resources that were freed in the last 100 frames. It is reported similarly to an active resource, as you can see here, only in this case, only resources directly overlapping the page fault address are reported. So let's dive a bit deeper into what the GPU crash debugging flag does. First of all, the CPU stack will not provide any useful information. Whatever command that was scheduled on the GPU that caused the crash was scheduled a long time ago. We need to know the actual state of the GPU at the moment of the crash. There are many different ways to do this, and they differ per platform. So let's start with PC. On PC, there's a wide selection of tools. The first tool is called DRED, Device Removed Extended Data. It includes a lot of extra information and is handled by Windows. Then there is breadcrumbs, which is very similar to DRED, only it is implemented by the user. For Nvidia and AMD specific GPUs, there are specialized tools available, such as Nvidia Aftermath and Radeon GPU Detective. The tools on consoles are very specific to the platform. When the crash happens, you get a dump, which you can then inspect and view the state of the GPU in great detail. Typically, more information is available on PC, so if you can debug on console, I would recommend it over PC. So let's go deeper into the first tool available on PC, called DRED. It's easy to use and works on all DirectX 12 supported hardware and is already supported by Unreal. DRED inserts markers after every render operation. It's all automatic and gives little control for the user. But Unreal has recently added support for lightweight DRED. This tracks fewer operations and has less overhead, so can be more easily enabled by default. Below is an example of a command list reported by DRED at the moment of the crash. You can see in this case that it's completed 6 or even 7 operations when the crash happened. It, however, doesn't guarantee that composite traces is where the actual crash happened. So as I said, DRED stands for Device Removed Extended Data. It also includes page fault data, which can be very useful. It reports the address where the page fault happened, and it also, like Unreal, tracks recently used and released resources, only not in the 16 megabyte range as Unreal does. Here's an example of a report by DRED when a page fault happens. As you can see, it lists active objects and recently freed objects, all within the range of the virtual address where the page fault happened. So let's now go into Radeon GPU Detective. Radeon GPU Detective is more accurate than DRED or breadcrumbs. It has stricter detection, it instructs the driver to crash earlier and with more information. It also tracks resources in case of a page fault. However, as I said, you need to enable it at the driver level, as it requires special mode to operate in, the crash analysis mode, which will then provide you generally more information. Unfortunately, you can't run it on all hardware, obviously only on AMD cards, but also only on the latest RX 6000 and 7000 series. So let's now move on to Nvidia Aftermath. Nvidia Aftermath is the equivalent of Radeon GPU Detective. It's also already integrated with Unreal. Upon TDR, it generates a dump that can then later be inspected. It includes a lot more information on the GPU state that's typically available with DRED or with breadcrumbs. It includes register values and active warps. So it may be a good tool if you have an Nvidia GPU to debug an advanced crash. Like all the others, it tracks virtual addresses, but unlike Radeon GPU Detective, you can ship with Nvidia Aftermath. So now let's move on to the last one, breadcrumbs in Unreal. Breadcrumbs is the user-implemented equivalent of the last three. It requires manually deciding when and what markers to write and what information to store on them. DRED works similarly under the hood, but offers less control to the user. And in fact, there's an improved version of breadcrumbs coming to Unreal. So let's first have a look at the old breadcrumbs as they were originally implemented. They do have some downsides. The original breadcrumbs only report the last started or finished marker, which is not a lot of information and in some cases can be incorrect. Let us look at an example. Clearly here, what we see is an incorrect breadcrumb report. If command 0 caused the crash and we get the report when the TDR happens, the breadcrumbs would only report the last marker. So this marker would be after command 1. So we would only receive the information that command 1 was responsible for the GPU crash, which in this case would obviously be a red herring. Depending on the type of the crash, the time between the actual report can vary drastically. So let's look at the new breadcrumbs. We ported this over from Red Engine to Unreal, and it's already available on GitHub. So you may already have access. The new breadcrumbs keeps track of all scopes on a bigger buffer on the GPU. So let's go back to the previous example. In this case, command 2 caused a crash. But we have multiple breadcrumbs. We have breadcrumb marker A, and we have breadcrumb marker B. When we get the report, when the TDR happens, we get all active breadcrumbs back and their associated state. So let's look at an example what the new breadcrumbs look like. So here you see a crash, and it reports the hierarchy and the state of every single scope when the crash happened on the GPU. It is easy to see which pass was active. In this case, we see that actually 2 passes were active, the nanite hardware rasterized and software rasterized pass. Either of those could be responsible for the crash, whereas the old version, you would probably only see the software rasterized. It also supports the compute queue. So you don't just get the graphics queue, but you also get the same hierarchy and markers that were happening at the compute queue at the moment of the crash. So let us move to the implementation of the custom breadcrumbs. As shown before, all the markers have a hierarchy. We schedule markers based on the events pushed to the GPU profiler through RHI push events. RHI push events then schedules a write to a shared buffer. This shared buffer is written to using RightBufferImmediate and contains all markers. Here's an example of the same hierarchy you would see in the GPU profiler. You would get the exact same thing back in the GPU breadcrumbs. So how does it work? We pre-allocate a breadcrumb buffer at the start of the application. This buffer is 2 megabytes in size. It is created using open existing heap from address that allows the buffer to be shared between the CPU and the GPU. And it is still accessible in the case of a crash, even though the driver usually doesn't allow any more access to the GPU once the process has crashed. By default, we allocate this buffer of 2 megabytes. It serves as a pool from which we can add and remove stacks. A single stack contains up to 4,096 markers and is used to contain an entire hierarchy of scopes. These values were chosen based on a typical workload in Unreal. Depending on your configuration, you may want to allocate more or less size, and you can do it through changing these defines in C++. Before, I mentioned the RightBufferImmediate command. We use this to write markers to a breadcrumb stack. First, we pass in the address of the marker, and then the value and the mode we write in. There are a few states a marker can be in. First is the non-started mode marker state, which is 0, which is the default state. Then there is the active state, which means that the work has begun on the GPU, and then there's the finished state, which means that all previous work has completed on the GPU. There are 2 more values in case an error happened. First, there's the overflow. As I mentioned before, we only support 4,096 markers in each stack. If you go beyond that, the status will be overflow. If there's another error that happened, the status will be invalid. There are also 2 modes you can use to write markers to this buffer on the GPU. The first mode is marker in. Marker in only writes when all work scheduled before has started. Marker out only writes when all work before has finished on the GPU. So the actual write is deferred until all the work is done. So how do we keep track of stacks and markers? First, the command context is responsible for generating work on the GPU. It creates command lists and sends them off in payloads to the GPU. When we begin a scope, we then need to write the started state of a marker to the GPU. So here we begin. And then we need to first get the breadcrumb stack that we use to write the marker to. It may be that the current hierarchy or payload to the GPU does not yet have a breadcrumb stack. In that case, we go back to the pool and we reserve some memory that we can then use to write markers to. Once we've got the stack, we then add it to the payload. Once we have our breadcrumb stack, we can then add the marker to the stack and schedule the aforementioned RightBufferImmediate call. Now with each begin scope, there is also a matching end scope. This could, however, happen much later. First, we write the finish state to the marker using RightBufferImmediate, and we pop the scope from the stack. If the stack is empty and no longer referenced anywhere, we destroy it. The memory is released to the pool and can be reused for other stacks. So now that we have our stack and we write our markers, how can we use this data when a GPU crash happens? First, we need to retrieve all active payloads on the GPU and collect their associated stacks. We then iterate over all markers in these unique stacks, read the status from the buffer that's still available on the CPU, and we print their status to the log. So let's see how this works in practice. We have a command context with multiple breadcrumb stacks. Then there are multiple payloads, each associated with these stacks. When we submit a payload to the GPU, then the work there will start. However, we need to know when the actual work has finished. Thankfully, Unreal has a submission thread, which keeps track of all the payloads, and when they finish, will signal that they are done. So at the moment the payload is finished, we know that the GPU work has completed, and we can safely release all references to stacks that we have for that specific payload. Now, in some cases, payloads can also be merged. So in that case, we have to combine all references to the breadcrumb stacks into the merged payload. However, there are some things that can go wrong with this approach. For example, if we get a lot of breadcrumb stacks. As mentioned before, they always take memory from a pool in chunks of 16 kilobytes. One stack always reserves this amount of memory, and with certain workloads in the editor, it could be that a stack contains only a single command. So that would mean that even though we only use 4 bytes, we still allocate 16 kilobytes. So the solution we have for that is that we merge all these stacks together if they have less than 100 markers. However, this also means that they will be kept alive a little bit longer than necessary. The new breadcrumb system is a lot better than what was there before, but it still has some limitations. As I said before, the size of commands in game versus editor can differ drastically. In editor, the command list can get huge, and if we then run out of space, we might not know the actual state of the markers that crashed. If that happens, you can, of course, increase the buffer size to debug editor crashes. There's also a non-zero performance overhead to adding these RightBufferImmediate commands to the CPU and to the GPU. If you have a lot of scopes, such as in the case where you report mesh and material draw events, there will be an actual overhead. Dread by default enables it for every render operation, and that's why it's quite expensive. If you release a game and you wish to use the breadcrumbs in the wild, I would recommend reducing the number of scopes to make sure that the overhead is non-significant. And of course, as I mentioned before, vendor-specific tools are going to be more accurate as they have more direct access to what's going on in the hardware. So for complicated crashes, I would recommend using those over Dread or breadcrumbs. So now let's go and talk about how we report the crashes that happen when a GPU TDR occurs. I will go over how we group and filter breadcrumbs and automatically create Jira tickets that belong to a specific GPU crash. So we use the breadcrumbs as our primary method for identifying GPU crashes. First, as we transitioned to Unreal, we had a very simple system to track them. Every GPU crash was grouped in a single ticket, and we'd manually have to retrieve the logs to see what was going on. This was always a temporary solution, and we knew we had to do better. This is what a ticket would look like, as we would have the ticket based on the CPU call stack, which would be mostly the same for all crashes. So not very useful. So let's summarize how our new approach for grouping breadcrumbs works. First, we have a crash, and then we need to process the breadcrumbs, which means we will filter them and group them based on what we get back from the GPU and only select the relevant breadcrumbs. We then output this to log and upload a crash report. Then on the backend, we have a script that then parses this log, filters out the breadcrumbs, hashes them, and creates a ticket. We don't use page fault information to hash our breadcrumbs because unfortunately they are not available. We could, however, add this if we use Dread or Nvidia Aftermath or Radeon GPU Detective. So what did we do for previous games? We already, like I discussed before, we parsed the breadcrumbs and we grouped the tickets by active and last finished scopes. There's a lot of information usually in the breadcrumbs, so we don't want to use every single bit to create a unique hash and ticket for each bit of information, as it's simply too much. But we do want to group same crashes in the same Jira, as it will makes it easy for us to inspect and see what's going on, and also prioritize the most frequently occurring crashes. So we did the same for Unreal. As we ported over the breadcrumb system, we already had most of the backend code working, so we could reuse that to group the crashes. So we do it in a few steps. First, we parse the log that we get back from when the crash happened. Then we filter the breadcrumbs based on, as I said before, only the last finished and active scopes. Then we need to remove all dynamic data from the filtered breadcrumbs, as they would obviously cause different tickets to exist in our backend system, which we don't want. Then we generate a hash based on these filtered breadcrumbs, and we create the ticket. And we use the last active scope as the title, which is also what the original breadcrumbs reported, which can still be useful, but sometimes an incorrect report for what's going on. But as the title is only there to give extra information, it's not crucial. So let's go over an example of how we filter the breadcrumbs. Below, you can see a short but unfiltered log output from a TDR. The crash seems to have happened in Lumen. Specifically, the build page update priority histogram. A lot of information is reported here. However, not all of it is relevant to where the actual crash happened. So first, we remove all finished work except the last finished work. We do this for every scope in the hierarchy. This still gives us a little bit of context, but not so much that it gives useless information. The blue lines are the last completed scopes, and the red lines are the ones we remove. So this is what our log looks like after removing the finished scope. Next, let's filter the non-started scopes. So here at the end, we have quite a few non-started. And again, marked in blue, we can see the last not started scope, which we also include in our filtered stack, as it may give some context to where the crash happened and what kind of work was scheduled on the GPU. Once we remove the non-started work, we are only left with this very small call stack. But we can't yet use it for hashing. As you can see, there is still user-specified data in the log. The numbers of textures and buffers for the access mode paths, and for the Lumen scene update, we get the number of card captures and the megabytes of texels that are used. If we were to hash this, obviously we would end up with a bunch of different tickets, because likely this user data would be different for every crash. So what we do is really very simple. We simply replace all numbers with an X. It's very simple, but it works. Now the breadcrumbs are ready for hashing, as they'll be unique for every single crash that is the same. So what we do is we take this, we input it to a hash function, we get out some hash, and then we create the ticket with the name build page update histogram, as that's the last active one. Now here are some example crashes that we had in Jira. As you can see already from the title, it gives a hint to where the crash happened, either in the shadows or in the skinning or in Lumen or anything really. It's already giving quite a decent amount of information, where before we just had the information that a GPU crash occurred. However, it's still not perfect. There are still a lot of false negatives when grouping. Because the way the GPU works is indeterminate, we do not know what other active work can be going on. We also do not know which active work caused the crash. So it may be that the same crash still results in a few different tickets. There might be some ways we could improve this by doing some pattern matching. However, that's still work for the future. Also, as I mentioned before, right now we do not support page faults. The breadcrumbs, unfortunately, do not have access to this data, but tools like Dread do. So we could use these to log page fault information and perhaps resources that were in the range of the crash when it happened. Also, the crash breadcrumbs are not the most reliable. Sometimes you get information back that really doesn't tell us much at all. For example, command list all finished is the most frequent ticket. This happens in case that we get markers back and every marker reads as completed. This could be a driver bug or something else, we don't know. In that case, we probably need more advanced tools to dig deeper and see what actually happened. Also, sometimes we get back very tiny breadcrumbs that just contain very little information. Usually they do contain a lot of work going on, but especially in the editor, when a lot of stuff is happening, we sometimes get back very small results that don't tell us a lot of information. In that case, we use the same approach of going back to more advanced tools, or if we can reproduce it on consoles, we will do that, as that provides more information. So with that, it's the end of my talk. I'd like to thank the CDPR rendering team for giving feedback, and especially to Tim Green for his initial implementation of the breadcrumbs. And with that, yeah, we're a bit early, but thank you for coming and listening.